Hello and welcome back to Discrete Mathematics. This week we're going to be talking about propositional logic. Some of the things we'll be talking about today, one, sort of the differences between tautologies, contradictions, and contingencies, and how do you classify statements as one of those three things. We're going to go over some derivation rules. Those are going to actually be really important moving forward because we're going to use those in our proofs. And then the last thing we're going to talk about are proof sequences and strategies and kind of getting started with that before we move on to more laws and predicates and all that sort of stuff. So without any further ado, so propositional logic. Last week we talked a lot about truth tables, and truth tables are still going to play a role today, but sort of in making that transition. Truth tables are great, and obviously sometimes the easiest way of thinking about something when it's simple. But as things get more complex, they sort of become impractical. You're just going to have a really, really large truth table. And it makes more sense to be able to take those ideas and just sort of formalize a process or a system to, handle logic in the same way you would handle algebra or anything else, right? That we can sort of use symbols and rules to, make new claims about statements. And so that's the idea of propositional, calculus or propositional logic. It's that system of rules that we can use to discover sort of, create insights from new statements. So we'll start with sort of this, weird taxonomy of, statements. Tautologies, contradictions, and the most common are contingencies. So I said contradictions, right? Anyway, tautology is a statement that is true no matter what the components are. So, if you were to take, something, P implies Q or whatever, P and Q are components of that statement. They could have true, false values all on their own, right? And so what this basically says is that it does not matter what what the true, false values are for every single possible option. This statement is always going to be true. It is a tautology. It is always true. And so we can start looking at that just by looking at a truth table. So here is a truth table for a statement. P or Q implies P. Right? Sorry, P and Q implies P. So, P and Q are sort of the two components, right? They could have individual values. And so those are the two left columns. You see every possible combination of true and false values you could have for those two, I keep wanting to call them variables, but those two components, right? So then if you AND those, the only time P and Q will ever be true is when both P and Q are true. In every other case, it's false. But then you're making an implication, right? You're implying that P and Q implies P. Well, implication, when the left side is false, is always true. So for three of those cases, it's true. The only one we really have to worry about is the top one, where P and Q is actually true. We need to make sure that the thing on the right is not false. But of course, it's true because P is true in that case. And so P and Q implies P means that, yeah, that's always going to be true. That is a tautology. It's like, oh yeah, I had, peanut butter and jelly for lunch. Oh, so that you had peanut butter. Yes, I did. I just said that a second ago. This is going to be true no matter what. And so would be an example of a tautology. When something is a tautology, instead of having that single arrow, shafted arrow or whatever, we tend to do sort of a double arrow. That double arrow shows that this is not only, this doesn't just imply it, it's always going to be true regardless of the values of P and Q. So the notation A double arrow B is the same as saying that it's the same as saying A arrow B, and that's true in all cases. That is a tautology. There's also the sort of the other double arrow with the two lines sort of representing equality, and that is for the if and only if situation, where you're not only A implies B, but also B implies A. So, yeah, tautologies can also go both ways. So sometimes when you have a tautology in the form of C and D and whatever and whatever and whatever, implies E, or whatever it implies, we actually choose to do a different notation, sort of a large brace with all of the different things that we are assuming for this statement, right? These are all the things that are given. P, as well as P implies Q, that is a tautology that would imply Q. So yeah, basically there's an implied and inside of that brace. These are all the things that we are considering as given in our statement. It would be a lot easier if I choose an actual example. So here is a statement. P and P implies Q implies Q. And that is a tautology, right? But I guess we should actually kind of prove that. And we could do that with a truth table like we did last week. And so here we've got P and Q, every possible combination of P's and Q's, right? And then the next component, sort of the thing most inside the parentheses, is going to be P implies Q. So that we can just go through the truth table, figure out in each case what P implies Q is. The bottom two are going to be true because P is false. And so when P is false, we're not really making a claim that can be contradicted. But in the top case, right, if P and Q are both true, then the statement P implies Q is true. But if P exists and Q does not, that's false. So we've got the following truth table, right, or extra column to our truth table: true, false, true, true. Then we can sort of go, okay, well, let's look at the slightly bigger thing, which is P and P implies Q. So we have the P implies Q part in column 3. We have the P part in column 1. So we just have to AND those. And that would be only true when both of those things are true, which means only the top row is true, everything else is false. Well, now we're saying in our whole statement that that thing implies Q. We're kind of in the same situation we were before. For the last 3 cases, this is false, right? So the answer, the entire statement is going to be true sort of by default, because anything, false implies something. Well, we're not making a statement about when that's false. And so we only have to worry about the top case. In that case, both the sort of combined statement P and P implies Q is true, and Q is also true. So it's true in every case. It doesn't matter what the individual values of P and Q are, that statement is always true. P and P implies Q, which makes sense. That's exactly what you're trying to say, right? Like, if, I take something where it's like, this implies this, right? Like, if you study, you will get a good grade. You studied, that should imply you will get a good grade. That's the whole reason for the implication, that second statement. And so this is a tautology. It actually turns out to be a very famous one with a Greek name because it's like that old. It's called modus ponens. Modus ponens is it's like the affirmative. It's the affirmation mode or whatever. And so that is something that we will end up using later on. Like, why do a truth table for all of that when we just know, yeah, if I have a statement P and I have another statement that says P implies Q, well, then what you're saying is, if these things are there, if we assume these things, then we can assume Q. Anyway, it's a tautology. We'll use it later in proofs. By the way, it is related to kind of the opposite, which is if I have not Q as well as P implies Q. So the P implies Q part is the same. But I can either say, hey, if I have P, then I know Q. If I have not Q, then I know not P, right? Because you said P implies Q. If Q is not there, right, I know that P doesn't exist. If P is true or false, Q might be. But like, going backwards, the implication is P implies Q. If Q is not there, then P can't be there either. And so that's called modus tollens, which is Latin for denial mode. It's, again, going back to like Greek philosophy, a very old idea of a tautology. And so those are both statements that we can use because we know them to be true always, that we can use to sort of make statements about new, blocks of things that come up. So that is the idea of a tautology. A tautology is true no matter what the inputs are. However, a contradiction is kind of the opposite of that. A contradiction is false no matter what the individual values of the components are. So if your truth table ends up with all falses, right, this is never true. It doesn't matter what the individual values of P and Q are. This is always going to be false. Then that's a contradiction. This is a really simple example, but P and not P. It is impossible for something to be both true and false, right? It has to be one or the other. Now, we're sort of going formal here. In the real world, you can think of lots of examples where it's like, well, but it's kind of unclear, and that's the idea. It's unclear, but it can't actually be both true and not true, right? The exact same statement. And so this is a contradiction. If I have, a truth table here for my parts, P could be true or false. That means that not P is going to be false and true, and then the P and not P is going to be false in both cases because there's always going to be at least one of them that's false. It's a contradiction. Now, contingencies are kind of the normal statements. They are statements that have both trues and falses in their truth tables. P and Q, P or Q, P implies Q, P, whatever. These are just sort of the normal statements. And we call them contingencies because they are contingent upon the true-false values that are there in their components. So tautologies, always true. Contradictions, always false. And contingencies could go either way. So we'll get into derivation rules. Sort of using these ideas of tautologies, things that are always true, we can create rules out of them that allow us to sort of manipulate other statements to try to prove new things are true. So, there are two different types, equivalence and inference. Sometimes you'll see everything just sort of lumped together, but equivalence rules are kind of like what we described in the last week, right? Where the actual statements are the equivalent statement. They're sort of exactly the same. We're going to have a bunch of these. And by the way, these slides are a great way to make a cheat sheet because later on you're going to be using these when you create proofs. So, maybe I'll create a cheat sheet or I'll just collect all of these different rules that you can use to manipulate statements to try to get them to prove what you're wanting to prove. But double negation, right? The not of something is the something, right? And implication, right? P implies Q. We can convert that into not P or Q, right? Because one of those two things has to be true. If P implies Q, then you either don't have P or you have Q, because that's the way implication works, right? If one thing, if the antecedent implies the consequent, then you either don't have the antecedent or you have the consequent, one of the two. Then we have De Morgan's laws. De Morgan's laws, I think we talked about last time, but it's the idea of sort of distributing that not across an or an and. And so sometimes it'll be like De Morgan's first law, De Morgan's second law, or De Morgan's law of, there's different ways of saying it, but they're both the same thing. They do the same thing. When you distribute a not across something that's in parentheses, P and Q or P or Q, you get not P and then reverse the thing. So if it's not P and Q, it becomes not P or not Q. If it's not P or Q, it becomes not P and not Q. And that's just the way the truth tables sort of work out for it, right? Like, if I say that I am not, I am not wealthy and talented, then that would mean I am not wealthy. I'm not wealthy or talented. I'm not wealthy and I'm not talented, right? So, yeah, even in English it sort of works. I think that's what we talked about last week. Commutativity, ors and ands work like addition and multiplication, you can flip P and Q is the same as Q and P. Those are commutative. I keep wanting to put an N in that word. Commutative, operators. But a multiplication or a subtraction and division are not, right? So basically, you can flip the rules with and or. And then associativity is kind of like that. If I have P and Q and R, and they're all ands, I can actually put those parentheses wherever I want. I can put them over the first pair or the second pair. It means the exact same thing, so long as they're all connected by ands or they're all connected by ors. That works. If you have a mix of ands and ors, you can't do it. So the thing that's nice about equivalence rules is that they are the if and only if situation, right? It's a double implication. A implies B as well as B implies A. And that means that you can sort of use them in one of three ways. You can say that given A, we can deduce B, right? So you can kind of just go down from a step, as you're transforming this expression. Or given B, I can deduce A. But the other thing that I can do is I can say that given a statement containing A, I can deduce the exact same statement, but substituting B. So I can actually make a substitution with equivalence rules because they are equivalent. It's the same thing. It's, I can put a 5 or I can put a 2 plus 3 into a particular expression, and it's the same thing because they are equivalent. So here are some, a weird example that we can use. So if I know that if you are not broke and you do not have homework, then you can go out this weekend, right? That is a statement, right? So if you're not broke and you do not have homework, then you can go out this weekend. Then I can deduce using De Morgan's laws that if it's not the case that you are broke or have homework, then you can go out this weekend, right? I'm effectively moving the not out and putting those two cases, right? You're broke or you have homework in parentheses, as opposed to you're not broke and you don't have homework. I can say you're not broke or have homework. You can go out this weekend. Anyway, changing the statement, but it's the equivalent. Now the next one are inference rules. Inference rules are basically when you take a stronger statement and you can deduce a weaker statement from that. They are not like equivalence rules because they infer only one thing. In other words, because you're going from a stronger statement to a weaker one, that's okay. But I can't make the claim that I can't go from the weaker statement to the larger statement. So I can only do one thing with it. Given A, deduce B. It just goes in one direction. And there's a bunch of these, and these can also be used as justifications for steps in a proof. One is conjunction, right? P and Q is P and Q, right? If I'm given P and I'm given Q, right, according to our brace, the and is assumed. So I can actually write the statement as P and Q. Modus ponens, we've already talked about. P and I'm also given P implies Q, then I can deduce Q. Modus tollens is I shouldn't say the opposite, but it's the not Q implies not P situation. Simplification is if I have P and Q, which is kind of the first thing that we did, right? If I have P and Q, that can imply P. By the way, that can also imply Q, right? It's simplification. I know that both of these things are there. If we assume that that's true, that's a given, then we can simplify to either side if we need it. And the last one is addition, which is just that P will imply Q or Q, which is kind of a weird one, and we'll talk more about it when we actually use it. But it is also a tautology, in part because it's kind of off. So then we can use these to create a proof sequence, right? These different rules. And there are more rules that we will have later, but for right now, we can just start with these. And so a proof sequence is basically all of the reasons we can sort of justify that this assertion that we're making is true. So let's create one. The first statement A is given, right? So the thing on the left, we can assume that to be true. It's basically an implication, right? If this is true, then I'm saying that this must also be true. So the proof sequence is just a list of new statements so that each statement can sort of be derived from the ones that came before it and can be shown by one of these rules that it's true. And eventually you want to get your expression to look like C, look like the thing on the right, because then you know that, hey, if given A, or A may actually be a set of statements, I can go through and using these rules where we know it's always going to be true, I can get to C, then I know that C is also a tautology. So let's try one that's a little bit more complex. This is actually going to end up being the transitive property of implication, but we're going to assume we're going to be given P, P implies Q, Q implies R, and we're going to say that that implies R. You can deduce R from that. So here's the proof, right? First statement, P is given. You always have to put in your givens, right? So P is our first statement and it's given. That's a valid reason because it's one of the things that we're assuming. This has to be true in order for our statement to be true. P implies Q is given, Q implies R is given, and so then we can get to Q from modus ponens of lines of statements 1 and 2, right? P and P implies Q, the one we just talked about, and then we can get R, which is the thing on the right that we're trying to prove, from modus ponens of 4 and 3, right? Since we've proven Q, we can then say, oh yeah, well then I can use the last given to do the exact same thing in the exact same order to apply R. And so this is the transitive property, right? It's similar to transitive properties you've probably dealt with back in geometry when you're doing proofs. If I've given P, P implies Q, Q implies R implies X, whatever, then I can also imply X. Those things are transitive so long as you sort of connect the train. So this is, proof sequences should remind you a lot of what you did in geometry. You sort of write your T, make your statements on the left. On the right, you're giving your justifications. So here's one that is a slightly different one. If we have P or Q and we have not P, then we can imply Q. Well, why is that true, right? It's because one of them has to be true for the entire thing to be true. Both could be true, but we know that in the case of not P, the thing that must be true for P or Q to be true is the Q. However, we got to prove that. So how do we do it? We start with a given, P or Q. The second given, not P. So with that, we've got to find a way to try to get Q out of those two things. So one of the things we could do is take that first one, the first given, and actually turn P into a double negation, right? Because that gets us a little closer to something else. So we can say double negation on 1. Not of P or Q is the exact same thing as saying P or Q. Then we can do an implication on 3 in order to get not P implies Q. Because when you have the not of something or something else, that's the same as saying that something implies the other. Well, in this case, right, because we did the double negation, we got rid of one of the negations through implication, but kept the second one. So now we've got not P implies Q. Well, not P implies Q, we can just do modus ponens like we did before because we were given not P. If not P and not P implies Q, we have Q. I'm saying a lot of P's and Q's. Hopefully you can read it and it kind of makes more sense. But that's the idea, right? We're trying to take the thing on the left as given and use these rules to make it look like the thing on the right. And that's our proof. So some strategies when coming up with proofs, because it is not an intuitive process. Sometimes you will use a pencil if you're doing work, right? Because you're probably going to erase. Sometimes you make a step forward and it's like, oh, wait, that's not going to get me there. I got to go back. But one of the things you can do is sort of approach it from both ends, right? which is honestly a great solution for lots of things. Where you've got the things that you're given, you've got the things that you're trying to prove. Well, what if you just took this forward a step? I can kind of see like maybe I'm supposed to do this with it, and then try and go backwards from this one. Like, hey, from this I could probably have gone back from this, and then see if you can try and meet in the middle. It's a lot better than just starting from the front, starting with the thing on the left, kind of going in a direction, realizing, oh no, that's not going to work, going back, then going in a new direction, going back, going in. It's like, oh, if I can see what I'm aiming for, right, by trying to transform that thing on the right backwards, that might be a helpful thing. Might not be, depends on the problem. But, we'll try to work on it. And obviously, practice makes perfect. But regardless, that's our sort of strategy for proofs. Maybe do the forward-backward concept, hit it from both ends, and try and meet in the middle. All right? With that, if you have any questions, feel free to send me a message on Canvas. And, I will see you online.